Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, everyone. Welcome to Pre-Conference Episode 2021, second tutorial series. Episode 2021 holds pre-conference activities with online tutorial series on synthetic aperture radar, collaborate with IEEE GRSS, technical quality of instrumentation and future technology. IEEE Indonesian section and Masyarakat Ahli Penginderaan Jauh Indonesia. To boosting the knowledge of SAR technology for young scientists and students. Today, we are going to have three amazing speakers and interesting topic include remote sensing technology for mapping by Professor Muhammad Aris Marfai, and Big SAR Data Intelligence in InSAR and PolSAR by Professor Akira Hirose, and Deep Learning as Applied in SAR Imagery Interpretation by Professor Feng Xu. This webinar can be accessed in Zoom applications, and also this webinar is being streamed live on IEEE Indonesian YouTube channel. And also during webinar, our hosts or co-hosts are going to inform you on chat room about question and answer link application and e-certificate link. Please mute your speaker during this webinar. And this webinar are supported by IEEE Indonesian sections, GRSS, Institut Teknologi Bandung, Masyarakat Ahli Penginderaan Jauh Indonesia, Chiba University, LAPAN, and BPPT. And allow me to introduce myself. My name is Rika Hernawati. I'm from ITINAS Bandung, Indonesia. Okay, first agenda is opening speech by General Chair of Episar 2021, Professor Josapat Tetuko Sri Sumantio. Please to Bapak Prof. Josapat, the time is yours.
Yeah. You can see my slide?
Yes, sir.
Okay, yes. Thank you very much, all of the guests and also the lecturer. Yes, Professor Muhammad Aris Marfai, Professor Akira Hirose, and Professor Feng Xu. Yeah, and I think it's all of people waiting this seminar because the lecturer is a very famous professor. Yes, in this field. Okay, this tutorial is one of the activity of next the 7th Asia Pacific Conference on Synthetic Aperture Radar, or Episar 2021. That this Episar 2021 will be held in Bali Island, Indonesia, next 1st to 5th November 2021. For the detail, as you can see in this website, yes, and yes, this symposium focus from the synthetic aperture radar, but we also consider for Indonesian, especially in the Asia Pacific researcher and student to present the research in the field of the remote sensing. Yeah, we serve some session from the remote sensing. So it's not just from the synthetic aperture radar. Yes, of course, the synthetic aperture is our focus, but we also serve some specialization from the common synthetic, remote sensing field. Yeah, and it is in the call for paper. You can check in the website. And yes, it is in the second tutorial. Yes, in our pre-conference of the Episar 2021. It is in the online tutorial series, yes, on synthetic aperture radar, or SAR. Yes, we started from 26 February until 20 May. It is for long, a tutorial every 2 weeks. For the details, you can check in this website. Yeah. Okay, the lecturer, yes, it is from many universities in the world, yes, and very famous and the expert in the synthetic aperture. Please deliver to your friend and also your colleagues, yes, to join this symposium, especially for the student from Japan and especially from the Chiba University. This is one of the lecture that you can join this tutorial. It is 5 times, yes, and times 3 professor. It is totally 15 hour, and you can get the credit, yes, for the lecture of the remote sensing. Yeah, and yes, today we have famous 3 professor. Yes, first is Professor Muhammad Aris Marfai. He is the head of the Indonesian Geospatial Information Agency, or BIG. Yes, we want to know about the recent topic in Indonesia about an application of the remote sensing for the mapping industry and also on the mapping project by the Indonesian government. And next, Professor Akira Hirose from the University of Tokyo, Japan. He is also my friend, yes, and he is expert, yes, for the SAR image processing. Today, he will give the lecture entitled Big SAR Data Intelligence in InSAR and PolSAR. Yeah, and next also it is also my long ship friend, yes, from Fudan University, China, yes, Professor Feng Xu. Yes, thank you very much, yes, to join us, yes, today. And he will give the lecture, Deep Learning as Applied in SAR Imagery Interpretation. Yeah. Okay, don't forget, before I close, it is in the important date. Yes, please remember that the abstract submission, please just submit the abstract first from the APSAR is deadline is April 30. Yes, please remember April 30, and then the paper submission is a full paper, yeah, submission is May 31st, yeah, and the notification is August, and we have still 1 month, yes, to prepare just the abstract. Abstract is less than 500, and you can prepare every day, maybe 10 words is enough. Yeah. Okay. And yes, the conference is 1st to 5th November. Okay. Thank you very much, and please enjoy the tutorial today. Yes. Okay. I will deliver back to Miss Rika. Thank you very much. Yeah.
Okay, thank you, Bapak Professor Josafat. So I remind again that please send your abstract before April 30 on 2021. Okay, without further ado, let's get started to our first lecturer from Bapak Profesor Muhammad Aris Marfai. Assalamualaikum, Bapak Profesor.
Waalaikumsalam.
How are you today?
I'm fine, really fine. I hope you also.
Yes. Okay, it's such an honor to meet you here, sir. And Professor Muhammad Aris Marfai is head of Geospatial Information Agency or Badan Informasi Geospatial Indonesia. To Bapak Professor Aris, your time is about 1 hour and then followed by QA sessions. Please, the time is yours.
Yeah, thank you very much, Mbak Rika. Allow me to share my screen first.
Sure.
And I hope you all can see this screen.
Yes.
Is that already there? Okay,
yes.
Thank you very much. The Honorable Professor Josafat, Professor Akira Hirose, and Professor Feng Xu, who are the speakers today. Also, the dear Mbak Rika, Pak Sony, and others participants, and also the participants in YouTube. Today, we are very glad to have you all here in the what they call pre-conference Asia Pacific Conference on Synthetic Aperture Radars. And this is the tutorial number 2. Let me introduce myself. My name is Aris Marfai. Now I'm working in the Geospatial Information Agencies of Indonesia, or you can know it as a BIG. Previously, I'm working in UGM, and Pak Josapat, one of our close friends. We have collaborated since might be last 10 years in the University Chiba and the University of UGM. But just this year, I moved to PIG, and now my task is about to do mapping in Indonesia. Therefore, our topic today is remote sensing technology for national mapping. I don't know how to click. Yes. My topic will be how we can utilize the remote sensing technology, especially to fulfill our task, which is what you call it, or what we call it, base map or base or topographic map of Indonesia. Before we start, I would like to briefly introduce our agencies first. Previously, you know us as Paku Surtanau, the survey and mapping agencies of Indonesia, which is start from 1970. But then in around 1997, we introduced the airborne synthetic aperture radars to do the topographic-based mapping. And this is the first time we use the SAR for the mapping and to create the map. And then since 2010, according to the Indonesian Geospatial Information Act number 4, 2011, we changed the orientation of Paku Surtanau and we set up the new agencies, what we call it, the Indonesian Geospatial Information Agencies. And then from then on now, we are now focusing on large-scale based mapping, which is in a scale 5,000. As you may aware that to do this mapping in a very big scale, this is quite a challenge for Indonesia, not only because of our very large area, but also we are facing with the challenge of the technology that we should use, as well as the challenge with the human resources on our side as well. But anyway, we should do this because the first thing we should do the large or big scale mapping using the several technology. The first, since 97, as I mentioned before, we use the InSAR technology here. And then we believe that to fulfill the large scale, which is 5,000, we should do the several combination. Why we need the 5,000? Because, for example, this is part of the solution on many development agenda in Indonesia. For example, that will be part of the answer to do the detailing spatial planning, for example, to have the permits to do the infestation, boundary dispute, disaster mitigation, etc., and so on. Therefore, we need these 5,000. And there is the suggestion to still keep the ideal photo and lighter, especially on the area of interest, to keeping our what you call it, the precision and also the quality. Therefore, if we have a look the matter of facts of area of interest in Indonesia, in the national wide, we have a 1.9 million kilometers square, which is consists of the urban, rural, and forest. So our task in PIG, actually, we should do the base geospatial data, including the 5,000 scale, 1,000 scale, 25, 50, 100, and so on. To do this, we should do the combination of the technology, for example, the aerial photo and lidar, because this is very prominent, what you call it, technology to do the best and the good quality of the data, especially in the urban area with a very detailed and very precision, etc., and so on. But other thing is, we could not do this for entire Indonesia, otherwise it's too costly and there's take many time, etc. and so on, especially for the forest area and rural. Therefore, we combine with air PolSAR and then as well as the images. So there is a matter of fact of the thing that we have to do now. If we have a look at the availability of, let's say, the 10,000 scale, we are not yet in a 5,000 scale. In 2010, for example, there is only several areas that we cover already with the different sources. For example, this area we do on 2011 near the Aceh. We using aerial photo, but also we use SAR, for example, in 2007, 2006 in some part of the Sumatra, but other parts, 2 parts in Java, for example, we do very long time ago using aerial photo, for example, also in Bali, etc. and so on. So based on this data, actually, we still need more to complete our mission. And according to the RPGM, which is our long-term development plan, we should do this until 2024, which is quite short for us actually. And therefore, then we see also that fortunately actually, the availability of InSAR data in our office up to 2012, we already cover several parts. For example, we do almost entire Sumatra in 2012 with 0.6 meter using ORI. And also the entire Java, actually, we have finished this SAR data. But still other places, for example, the new capital city, Efitiso, in Kalimantan, as well as in Halmahera, also in Papua, there's not yet on this data. So I mean, we still to work hard to finishing those thing up to 2024. There is the several data that we finishing, for example, 10,000. This map was created by photogrammetrically from 2008 InSAR data, supplemented by the information from the QuickBird images. It means that you are using the combination. We see how powerful actually, for example, QuickBird image to help us also to do the fish map on the 10,000 scale. Another data, for example, we have also the availability of high resolution auto-rectified images up to 2020 with a pixel size 20 centimeters. And again, this not yet cover all of the entire of Indonesia. Therefore, we still need more effort to do this in our part later on. Our challenge is actually in the future to do this mapping as we are aware about this Indonesia. First, the area is quite a very large area, I would say 1.9 million kilometers square, and we are consist around 16,600 small islands. So it means there is also, if we do the field checking to do the mapping, for example, that will be also to be considered of this one. And also our population right now, based on the 2018, for example, we are no more than 260 million population, and with the population density quite high, 150 more kilometers square, 150 people per kilometer square. Other challenge is, some part is highly covered by cloud. And this is really our consideration to do the mapping by remote sensing, optic, for example, etc. and so on. Therefore, the InSAR is one of the solutions to do that. And also another complex environment and landscape. I will explain you how complex our environment later on. This is the cloud window of Indonesia. If we have a look at this, we can see that some of the Indonesia are really covered by high level clouds. and only some places are covered by a clear window or no cloud. So this is also the problem. If we do the business as usual using the remote sensing from satellite, for example, here without using the aperture radar. So to penetrate the cloud is actually one of the problem. And this is another example challenge in us, which is the complex environmental challenge, because you may know that in Indonesia we have many type of settlements, starting from dense slums up to the high storage building, lunch building, slum area, etc., and so on. And this is quite challenging to the interpretation, especially on the dense slum settlement, as this is seen in the picture. Also, for example, another problem is we have some places, houses, especially in the rural area, covered by trees from above. So it's also quite difficult to do the mapping, various type of roof, etc., and so on. This is still the agenda that we have to finish related to the mapping. And the next thing that I would like to, and this is the typical large-scale topographic-based mapping technology that we use so far in our agencies. As I mentioned before, we are using the combination, not only the aerial photo, but also we use the satellite optical images. Though one and another, they have the advantage and also the disadvantage. For example, the aerial photo, with the input of the stereo images pair, we could do the 3D stereo photogrammetry, editing, and attributing. Using the LiDAR, we could do the stereo image pair up to the classified point cloud LiDAR, etc., and so on. Using the airborne SAR, we could also do with the DSM and DTM, and also the optical imageries with the mosaic ortho image. So there is the typical large-scale topographic-based map technology that we use in our agencies. Just to inform you that actually so far up to now, in the last 5 years, we just finished less than 2% of the entire area of Indonesia on a mapping of the scale 5,000. So therefore, in the next 4 years, we should finish another 68%. So we will try this with the combination, as I mentioned, some part using the aerial photo, airborne SAR, and other part using the high resolution images, and so on. But other thing, in our agencies, we are using these images not only for base map, base information mapping or base mapping or topographic base mapping, but also in our agencies in BIG, we have the task, we have the obligation also to do the thematic mapping. So therefore, we utilizing, for example, SAR, LiDAR, optical image to do the thematic mapping. Just to give you an example, we are doing also the coastal flooding and inundation mapping using the SAR images. For example, in the part of the north of the Java coastal area, because as you know you may also aware that the coastal subsidence in some part of the Semarang city, for example, that could be up to 10 centimeters per year. This is really incredible. So to do this, we use mapping using the SAR image. So this is the example how we use the images to help us to do the thematic mapping. The second, we are also contributing on the post-event rapid assessment mapping. For example, after the earthquake August in Lombok 2018. So this rapid mapping, we use the unmanned aerial vehicle and field survey to identify the distribution of the settlement and infrastructure damage. So in the near future, we should also try to, for example, how the UIV, for example, as doing also by Prof Yos, can bring the sensor of the radar, synthetic aperture radar, to fly over the prone area of the disaster to collect the data more rapid, more speed, etc., and so on. Also, another case, we use the post-event rapid assessment mapping of the earthquake after the earthquake 2018 in Palu Donggala. And this rapid assessment mapping is combination between the satellite images, ground survey, topographic map, and also the national dams. And this was also to map the affected housing and building, and we are incorporating by that and with the BNPB, for example, the National Agency for Disaster, to provide them with the another example is we do also the national rice field map, for example, derived from SPOT 6 and 7 satellites in Indonesia. As you know, you may also aware that our field rise time by time is decreasing, and we need to know exactly how large, how potential our field rise in order to support the SDGs number 2, for example, what we call it, no hunger for the people. And this is also another example of how we do the thematic mapping using images, for example, related to the ocean and ecosystem derived from multiple sensors. Here in this activity, we try to characterize of water and salt field, also algae macro, mangrove, seagrass field, basic substrate, coral reef, especially also to identify our small islands. And this is also what we have done in the last 2 years. Another example, we also utilizing the images to do the national palm oil cover map in Indonesia, as it is also mandate or part of the goal of the APT7, which is affordable and clean energy. So, in general, our agencies nowadays have tasked to do the base topographic mapping in various scale, but we are now prioritizing in many technology in acquisition data, which is we use the LIDAR, we use aerial photography, we use the satellite images, etc., and so on, for different areas. Priorities also should we have the responsible on the thematic mapping related to the information geospatial related to the thematic, for example, disaster, for example, the environmental monitoring, for example, the productivity of the field rise, etc., and so on. So hopefully some agencies, professors, and colleagues who have the advanced technology using the collaboration, I do believe that we can cover in the next 4 years to come to have the peace map in the resolution of the 5,000 scale. So I think that is from us how the remote sensing technology are using for mapping. in our agency, especially to fill our task. And we can also continue with the discussion if this may some question. Thank you very much. I should end up now, and then I'll give to Mbak Rika.
Okay, thank you, Professor. Would you mind if we continue to question sessions, sir?
Yes, please go ahead.
Okay, I'm going to share screen. We have a question in application link. Okay, Bapak Professor Aris, we have two questions from Muhammad Arif Munandar. He said that we have many data from different sources like photo, SAR, and LIDAR. Could we combine the data with different sources? How BIG do it? Thank you.
Yeah, that's actually very nice question from Pak Arif Munandar. The point is like this. In order to fulfill our task for the entire Indonesia, we should know and we should consider that we have the really complex features of the Indonesian to be mapped. In the urban area, with very dense density objects, we should do the mapping using high quality of the data with very prominent acquisition data techniques, which is, for example, we using the airborne and SARs. But we know that this might be also costly for us. Therefore, for the area in a rural area and less complicated like forest, though we should do the mapping, we could also combine with other technology which is cheaper, for example, using aerial satellite, etc., and so on. If the question, could we combine, actually we are not combining the data, but we are combining the output into the puzzle. I mean, if we do the urban area using the airborne and we use rural area and forest area using the images, grid images, but the result come up with 5,000 scale resolution of map. So then we can put it as mosaic complete for the Indonesian. So actually, we are not combining different sources, but we do in a many way of different area. So depend on the how complex of the area is.
Okay, thank you, Professor. And then we continue to the second questions from Muhammad Isa. He said, Professor Aris, BAG has subsea pipelines and cables routes. How about the on-land pipeline routes? Is there any plan to have it in BIG's future agenda?
Yeah, thank you, Bapak Muhammad Isa. The thing is actually the pipeline and cable routes not belong to BIG, but BIG, one of the agencies who are responsible to do the mapping of these pipeline and cable routes. Last 2 weeks or 3 weeks, actually, we have the meeting with the coordinator minister of the what you call it, maritime and investment to organize and to coordinate how we can manage the pipeline and we can manage the what you call it, cable routes in under the sea more on the better way. And our task is to map the routes itself. The question is how about the online pipeline routes? Yeah, actually the pipeline routes also not belong to us, but as this is also mentioned in the Undang-Undang Number 4, which is 2021, Peraturan Pemerintah Number 45 2021, which is we have to do the map, base map on the 5,000 resolution, which is in the 5,000 resolution also include the infrastructures. So if the land pipeline is part of the infrastructure, though this is managed by other agencies, for example, Telkom or Info, etc., and so on. But if this is there, then we have to map this pipeline route. So actually, we are mapping based on the data availability, or if it is seen from the our sources, which is from InSAR or from satellite, then we have to map it.
Okay, thank you, Professor. Well, next we have Ardiati. What are strategies to produce large-scale mapping within 4 years until 2024?
Yeah, that's actually a very good question. First of all, in the term of the technology, we should do using the artificial intelligence, object-based identification, computerized-based interpretation, etc., and so on. Then second, in terms of the acquisition data, we should also combining the acquisition by airborne, LIDAR, satellite images, UAV, etc., and so on. So we do the combination in acquisition data, we do the automatization and the interpretation to have the mapping. The third, in order to do so, all those things, we need more resources. For example, the budget. Yeah, this is one of the constraints to finish in the fourth year. Therefore, the government, we born the regulation, which is just recently born, peraturan pemerintah, peraturan presiden, presidential decree number 11/2021, which is the cooperation, the national government with what you call it, Badan Usaha Milik Negara on the national enterprise agencies. So therefore, right now in this moment, this week and maybe next 2 or 3 weeks, we should finishing our agreement with BUMN to come up with the strategy how we will do this. This is the first. The second thing, actually, we have already the roadmap to do this in the next 4 years. For example, this year, in cooperation with the BUMN, we will cover the entire of Java first. And then the next year we cover, for example, Sumatra, and then another islands, etc., and so on, up to 2024. But other thing, we also try to utilizing the data that we have, for example, into the monetizing or do the what you call it, capitalization of this data. Therefore, the industry can come with this, for example, the digital industry, etc., and so on, can generate money from this one, and this will be as part of the resources to continuing our mapping, as well as to continue our maintenance of the data, updating on the data, etc., and so on. So our task is actually part of the big goals, which is how the information geospatial is used on the commercial sectors, will be used on the private sector, how we can push the digital industry also using the data, information geospatial data that we create in the next 4 years.
Okay, thank you, sir. So maybe this is
good. This is very nice question. If you allow me to answer,
sure,
is it possible for BIG to collaborate with Gojek, Grab to make participatory mapping, or use RPI as the map of their application? Yes. May I answer this question?
Sure, sir.
Okay, thank you. RPI. Up to now, we have RPI mostly into 25,000 scale. So to do this in application, yes, you can, but actually we need more detail. Therefore, we will provide the detail RPI in 5,000 or high scale, and this is prominence data to do in application, to do in the business, industry, etc., and so on. Should we or can we in cooperation with Google, Gojek, and Grab? If it is thematic map, the answer is yes. But if it is the best map, basic map or base topographic map, as this is a part of the government regulation that the base map should be owned by government, created by government. So we should create this, as this is part of the secret of the nation. But for sure, for the thematic map, we can incorporate with the Google, Gojek, and Grab. The second thing is, later on, once we are finishing with 5,000 scale, it means we have already our very huge, valuable, and big information, geoinformation data. And therefore, we can utilizing this in cooperation with the private sector to do the many things, monetizing this using the application. You can imagine if we have many applications in the near future, those all on the application not anymore based on Google Map, but they would be based on our map. That would be our pride, for example. Now we are going to this part.
Okay, thank you. Maybe this is one last question, sir.
My
One
pleasure.
more.
Yeah, Prof, is it possible for TEMNAS to be updated regularly? Because it's very useful for monitoring land, one of which speed area due to the landform. Thanks, Pak Tommy Ardiansa. Yes, the answer is quite simple, yes. And therefore, in the next 4 years, our base map is actually not creating only the topographic map, but include on this information would be the digital terrain model, the digital surface model, 3D modeling. So we, for sure, we will update the TEMNAS based on this. And using this more output, we can create many, as I mentioned before, we can create many things, information, application, facilities, industry, etc., and so on. So therefore, also our task in BIG is also to support, to facilitating the industry on geoinformation to be more developed using our data and resources. Thanks, Mbak Rika.
Okay, thank you, Professor Aris. Before Professor Aris leave from this room, how about we take a picture first with Professor Aris. Please to the audience to open your camera. Okay, follow my. Okay, co-host, please help me to screenshot all windows. Okay, thank you. Okay, let's start. 1, 2, 3, smile to the camera. Okay, next slide. Okay, 1, 2, 3. Okay, we have 6 slides. Okay, for third slide. Okay, thank you. Thank you so much. Thank you so much, Professor Aris. It's such an honor to meet you here. I hope you are always in a good health. Thank you so much, sir.
Yeah, thanks you also, Mbak Rika, Professor Josapat, Professor Akira, Hirose, Professor Feng Xu. If you allow me, then I will leave this session. Is that okay? Okay, thank you very much.
Professor Aris. Yeah.
Yes, thanks, Prof. Josapat. Please keep healthy.
Yeah.
Yeah. Bye-bye.
Goodbye, sir. See you next. Okay, to all the participants, once again, if there are any question to our speaker, please follow the application link on chat room, and e-certificate are going to publish or are going to available before this webinar ends. And also, you can still have the recording of this webinar on IEEE YouTube channel, and please don't forget to subscribe it. Okay, let's continue to our second speaker. We have Professor Akira Hirose from Tokyo University. Konnichiwa, Professor Akira Hirose.
Konnichiwa.
How are you today?
Yeah, fine. Thank you. And you?
Okay. I'm very fine. Thank you. I'm great. Yeah. Okay, thank you for coming to our webinar. Please, your time is about 1 hour. And then after that, we are going to continue with a QA sessions. Please, sir, the time is yours.
Okay. Good afternoon, everyone. I'm Akira Hirose, University of Tokyo. I'm very excited to hear the Professor Aris lecture, showing many observations and observation plans in the near future. My talk is mainly about the post-processing of the measurements. These are data intelligence in InSAR and PolSAR, and I focus on InSAR this time. This is the outline. First, I mentioned briefly the importance of data structuralization. And then, well, I'm working on neural networks for years. And well, I introduced a convolutional neural network. I think many people are working on this one, but please check what you know and what you are working on. And then example of the use of the neural network in the structuralization. So land shape discovery using complex valued convolutional neural networks. And the concluding remarks. Okay. On the left-hand side, you see the optical image of Kyushu Island in Japan, showing Sakurajima area. This is an island, but connected to the big island. And this is an optical image. So we can see the mountains are green and the towns are well, gray or white. And here we have Shinmoedake Mountain. It is a very new mountain, very active, and we can see the smoke. On the right-hand side, I show the Aris-2, PolSAR-2 image. Well, in this case, we use microwave of about 1 gigahertz. Then it is not colorized, but we can see the intensity of the backscattering on the surface. And at the Shinmoedake mountain, we can see the small cones, volcano summits without any clouds or smoke, because the microwave goes through the smoke. We can see under the smoke. So in this way, the data are very different from this one and from another one. And well, as we saw in the Professor Aris presentation, that Earth is a water planet having much clouds. So it is very important to see beneath the clouds, or in the night, by using the microwave, we can see the land surface. And at the same time, it is very noteworthy to say that we can obtain the phase and the polarization information by using the microwave, because we generate the microwave sinusoidal wave and transmit it to be scattered on the surface of the Earth, and we observe the backscattered wave. Then the phase and the polarization are very important. If you attended at the previous lecture 2 weeks ago, I think, Yamaguchi-sensei presented many data and weight of analysis on the polarization information. Well, this time I focus on the InSAR, interferometric synthetic aperture radar, to observe the phase of the wave. Well, when the satellite is flying here, at this point, this one, then it transmits wave, microwave, to observe this point of the Earth, and it receives the backscattered wave here, almost at the same point. And then the wave includes the distance from the satellite to the surface, and also from the Earth to the satellite. So this is the go and return way. But at the same time, the phase also include the changes at this scattering point. It depends on the scatterer's nature. But anyway, it includes the distance information. And the next visit of this satellite will be very near to the first one, but a little different position. And then it gets the same information, but a little different. And then the scattering phase change is very similar to the previous one. So we can cancel the phase changes at the scattering point. Then with a very simple calculation, we can get the distance of the satellite from the satellite to the Earth, and also the height of the land in this way. So we can get the land height map very precisely by using the information of the phase. So this is the comparison of optical observation on the left-hand side again, and the microwave right-hand side again. So on the left-hand side, this is well, Tohoku area in Japan. You may remember the very big earthquake 10 years ago occurred in Japan. And this area suffered from tsunami. Before the tsunami, the optical observation shows this photo. The red one shows the green, actually, the trees on the mountain here. And on the seashore, there were many houses before the tsunami. But after tsunami, the water came up to this area, and we can see the flooded area as the difference in the color. Many people suffered from this tsunami. So in this way, optical observation is very important. But the microwave, we have already watched the intensity map. But this is a phase map of the interferogram made from the two observations before and after the earthquake. So this point star shows the center of the earthquake, and it was very big, magnitude 9.0. And after that, we can see the fringes showing the phase changes. In this case, the 2 pi corresponds to about 11 or 12 centimeters. So we can count the fringe numbers, and we can say this is 1 meter, 2 meter, and so on, changes before and after. And we can also see the fringe is very dense near the epicenter. In this way, we can observe the land surface height changes very precisely. Volcano is another very important field of application. In March this month, Mount Sinabung erupted. Well, Indonesia is a country of volcanoes and earthquakes, and the situation is very, very similar in Japan. We have many volcanoes and many earthquakes every year. This is an example. About 2 years ago, we had a not so big eruption, but an eruption in Gunma prefecture. There, we have Mount Shirane. It is an active volcano, and it is located in a sightseeing place. We have a ropeway very near to this summit. Ropeways. In the winter season, many people come to this site to enjoy skiing. And here we have golf field and onsen, Kusatsu Onsen. Onsen is hot spring. It's a very famous sightseeing area. And 2 years ago, we had eruption of a volcano. Well, this Mount Shirane had many eruptions in these years, 1939, 1983, and so on. And the government decided to put GPS equipment and 10 GPSs and 5 monitoring cameras around this mountain. But this time, 2 years ago, another one erupted, Moto Shirane-san. This is Shirane-san, Shirane, Mount Shirane. This is Mount Moto Shirane. The name is very similar in Roman or in Japanese or Chinese characters. The distance of this mountain to this mountain is about 2 kilometers, only 2 kilometers. But we had no GPS, no cameras here in this Moto Shirane-san. And therefore, we didn't know anything before the eruption. We couldn't catch anything. So many people or surprised to see the sudden eruption. Well, GPS is a very useful. Monitoring cameras are also very useful. But if we observe this area very frequently with the SAR system, satellite SAR system, then we could have catch something, some information in the observation. This is the present state. In the near future, probably a public service person at the disaster mitigation section in a very small town will want to find volcanoes similar to a recently erupted one. For example, this one. And he or she may also want to know the changes in the shape, because in many cases, a mountain gets fat before the eruption because of the movement of the magma. Then, if this type of observation and discovery is done automatically, then it's very useful for raising an alert. Well, presently, the space agency and the government, National Research Center and universities work on the observations and the data analysis in cooperation, and the data, processed data is delivered to the end users, government, farmers, breeders, forestry people, economists, geosciences, and so on. They are very useful. And interface companies are also very active. This is very nice. But in the near future, we'll work more closely together. The farmer, for example, may want to access directly to the data to obtain the changes in the shapes of the land surface or other moisture-related data. So we have to work together. Then it is very important to prepare the data ready. That is, if we want to gather mountain data similar to this mountain, then we will access the data center to get the similar data, this one, grouped beforehand based on the feature. In this case, the shape of the mountain and also the changes of the shape. But this is one aspect. We have to structuralize the data in many feature directions. So we may use the shape of the land, we may use vegetation, we may use just the intensity of the dark scattering, and also we also use the infrared visible light observation data. And we will put the data in a grouped way. So this data is similar to this data, then they are located very near in one aspect. In another aspect, they can be very separate. And if a person, end user person, want to extract some data out of this amount, then he will prepare a certain aspect and get the data useful for him or her. So this preparation is the structuralization, and it should be done in high dimensional feature space based on many physical features as well as very social or human related features. Then the database will be more useful for the eruption prediction, disaster monitoring, glacier monitoring, also the CO2 evaluation, biomass, harvest prediction, and so on. Okay, and that kind of works are done with the AI, modern AI. We have very strong AI these years. And this AI is a little different from the, say, 20 years ago AI. 20 years ago, people constructed AI systems based on the logic and rules and the relationship between or among the data. People labeled the data manually, almost manually. But in these years, the situation is very different. We use neural networks. This is the base of the AI, modern AI. And in particular, we often use deep learning processes. Probably Professor Feng Xu will go into the details of the deep learning. I also check the very superficial briefly. So convolutional neural network is used here to find Omuroyama-like landscape. So we want to find this landscape in the world automatically. Omuroyama is a Japanese name of mountains of this kind. And the meaning is very big storage mountain, big storage mountain. Because the ancient people are believed to use this mountain as the storage of the crops. And this is a scoria cone in English, scoria cone. So it is a eruption output, well, drain or something like that. Okay. Well, neural networks. Some of you or many of you are familiar with neural network. Well, if so, please check what you know. Neuron. This is a neuron. We have many, many neurons in our brain and also in our nerve systems. And this is the soma, and the cell has many dendrites, which works as the input terminals. And the output is called axon, which transmits the signal to another neuron. And at this axon, the signal is weighted to the next neuron. And the neuron gathers the signals to sum them up. So the situation may be expressed in this type of equations. The signals are xi, x1, x2, and so on. And the weights are w1, w2, and so on. And y is the output obtained at this action point. Well, about 70 years ago, Macaro and Pitts, two persons, researchers, proposed an official neural, or official neurons. That is, they assumed if they observe many pulses per unit time, they assume the signal is 1. No pulses, then the signal is 0. Median, okay, it is 0.5 or so. In this way, they constructed the neural network as a mathematical network. 70 years ago, at the same time, the people developed ENIAC and EDVAC and other first digital computers, electronic computers. And there, the people used 1 and 0 electronically. This fact should have made great influence to this official neuron proposal. But anyway, this is the neuron. So simplified or modeled so that we can use mathematics. So then the neuron, or one single neuron, can work as a classifier. How? Okay. We have two groups of data. This is, say, paprika, green paprika. And this is, say, apples. And we want to classify these two things, paprikas or apples. How we can do that? We check the size, big or small, size of the paprikas and apples. The data is shown here on the X1 axis. And we also check the weight. Weight is shown as X2. They are the data. And what happens? Well, these data are fed to these inputs, two input terminals. And this neuron generates this output. The Macaro-Pitts model neuron do the following thing. They are the new input signals, X1, X2, and they are weighted with these weights, W1 and W2, and then they are summed. In the equation, W1, X1, and plus W2, X2, this is the output. Well, we often introduce a nonlinearity here at the output of the output signals, but we omit it here for simplification. This is the output. Then this equation shows this line. Well, if y is 0, we put y at 0, then we get a line here. On the upper half, we have positive y's. On the lower half, we have negative y's. And if we choose the w's in the proper way, then we can get positive output y for all the paprikas. And we get negative value as y for all the apples. That is, we are successful in the classification. And the decision of the appropriate W's is called learning. This is the neural network learning process. So I know that many of you are familiar with this process, but please enjoy. Okay, this is the simplest case. So the task is called linearly separable. That is, these two groups are separated with a simple linear line. Then, what happens for this case? Well, we have paprikas here, and we have apples here, but we have other apples here also. Then, we do the follows. We use this neuron, Y1, to obtain Y1 by putting this line here, the same one. And Y2 here, another one, by using another neuron. And Y3, another one, another neuron. And then we gather the outputs, these three outputs, to obtain only this triangle inside. This is the total output. We can do this by applying a certain learning algorithm. So the key point is to prepare the, this layer. We call it hidden layer, because we cannot see this hidden layer directly from the input terminal layer or from the output neuron layer. So if we have one hidden layer, then we can deal with non-linearly separable tasks. If we prepare many hidden layer neurons, then we can get more complicated situations solvable. We can obtain paprikas also here, anywhere. And in this case, in this sense, two layers, so one hidden layer and one output layer is sufficient for any task. But about, say, 40 years ago, many people were confused. On our brain, on the neocortex outside, the most outside layer, it has 6 layers almost everywhere. 6 layers. Why? 2 layers are enough mathematically, but our brain has 6 layers. And this is the trigger for us to develop the deep learning. Deep learning means many layer neural networks. Fukushima sensei in Osaka University, or at that time, he was with the NHK, broadcasting company, so not national, but almost national broadcasting company in Japan. It has a very big research center inside. He was working on the visual and recognition processes in the human beings. And he paid attention to the locality of the connections as well as the layers. Well, we have 2 layers here in this figure, but actually we have 6 layers. And the neural connections are often observed only locally this way in the layer, within the layer, respective layers. So it is a type of columns perpendicular to the plane layers. And he proposed a neural network, very novel at that time. Well, it is very useful. It should be very useful in letter recognition. Well, we want to develop a machine that can recognize this letter as A. And probably you understand very easily that if the A is a little shrinked or a little extended or a little rotated, then it is very difficult to identify the letter in a simple mapping to a signal vector X. Well, if we map this pixel value to the first X, this one to the second X, third X, and so on, and then we continue this mapping to the next row, next row, next row. This is a possible way of making a data vector. But if the scale is a little different or it is a little rotated, then the vector is completely changed. Then we can, or the machine cannot find the similarity between this letter and this letter. Fukushima sensei considered in our brain, this process happens. Well, the feature is extracted here. Well, this part is very specific to A. So the neuron or neurons extract this feature. And this part is also very specific to A. This part also, this. The length of the line is not so important. And if they are extracted, then by gathering these features, the brain can recognize A. This is the idea. If it works in this way, the recognition process is very robust, even if the A size is changed, bigger or smaller, or a little rotated. It's okay, no problem. This is the idea. So it worked very well. And the post system in Japan adopted this idea in the mail delivering system, and many countries did it. So this is the input image, and here we have the feature extraction layer, local feature extractor. So we call these local or Windows filters or kernels or something like that in these years. And also the translational movement is adaptively adjusted. If the position is a little different from the typical one, it's okay, no problem. The system will adjust the position. So they are the convolution and pooling layers. So this pair is repeated 3 times, and the output is obtained. And the convolution process is a process of inner product generation. So the neurons learn the inner product. And the pooling process realizes the tolerance in the space. And it works very, very well in the deep learning neural networks in these years. There are many variations, and they are modified for respective applications. Okay, then an example in the SAR or InSAR observation. So landscape discovery. Here we deal with the Aris-2 data, Aris-2 of JAXA. So this is the amplitude data showing Izu-Hakone area. Here we have Mount Fuji. I hope many of you know Mount Fuji. Most of Japanese like Mount Fuji very much. And this is Hakone area, sightseeing area with Ashinoko Lake. Here we have another lake, Yamanaka-ko. And this is the Izu Peninsula, Atami sightseeing place, and so on. The black area is the sea. This island is Hatsushima, I think. This is the amplitude image. And on the right-hand side, we have the phase in the color representation. Mount Fuji has a very simple fringes showing a very simple shape of Mount Fuji. Near the top, the fringe is very dense. It means that the slope is very steep. And we have another mountain, smaller one, Ashitakayama and Hakone mountains here. And on the sea, the phase is very noisy because we have only a small power reflection or scattering from the sea area. And this is the data. And we apply a convolutional neural network to find the Omuro-yama. We want to discover this shaped mountain. And the shape is represented by the phase. So we mainly deal with the phase or the complex value of the observed data. And then we employ complex valued convolutional neural network. So this is the input data, and we prepare convolution filters and pooling windows and so on. And usually we prepare a full connected layer here at the output to obtain a decision result. So the convolution is written in this equation, but the important point is the follows. This is the local window showing the local data in the input image. And if the local filter in the convolution layer is very similar, the data is very similar to the input, then this part, this neuron, generates a big output. If the data is not so similar, then the output is smaller. So in this way, the convolution layer calculates the similarity as the inner product. And in the learning process, by showing the teacher signals at the output with the backpropagation or something similar to backpropagation to obtain the teacher signals inside the layer, inside the neural network, then the filter value changes by itself to extract something meaningful to generate the output of the classification. So we can see the growth of the convolutional filters in the following view graphs. And teacher backpropagation is shown here in the equations, but it's okay. I skip it. Pooling. Pooling is, well, we will take max or average or something like that to absorb the translational mismatch in space. With the combinations of these two processes, the neural network realizes the extraction and classification of the features, local features. Then, if the local window size is not so far from the size of the mountain we want to discover, then we can extract the mountain or the position of the mountain. And in this particular case, we are not interested in the absolute height expressed by the phase value directly. Then we calculate the changes or the gradient of the phase in this case, but it is not so important. And that's why we have two input images or two input channels. So this is the data amplitude and actually with the phase. And we take teacher signals to apply the supervised learning. And in this case, we take node slopes here. This is the teacher signal area for node slope. We have Mount Fuji here, then we can get north slope area in a very simple way by choosing the area here on the north side of the Mount Fuji summit. Here is slope, south slope, west slope, and also flat. The flat color is not good, but this is the flat area, very near to the seashore. And sea area. And this is the Omuroyama teacher area. What is that? Okay, this is the area, Google Photo. This is an example of Omuroyama. In Japan, we have many Omuroyamas. And this is the typical one. And we use this mountain as the teacher Omuroyama. So this is the red area. Okay. And then we apply the learning process to the neural network, and we did the adaptive classification to this Izu Hakone area. We focus on the area 1, area 2, and area 3 in the following pages. In area 1, this is the teacher Omuroyama. And the red one indicates the Omuroyama-like shape is here. Of course, this is the teacher Omuroyama. Then we see the red mark. Okay, this is Omuroyama. But we have another Omuroyama, or another red area. What is that? Well, this is the same photo, Google photo, showing the teacher Omuroyama here at the center. But we can also find another Omuroyama here. Well, Omuroyama-shaped mountain. This shape is very similar to the teacher Omuroyama, but the size is smaller. Even if the mountain is smaller, the system, the neural system, is successful in finding this shape. So the convolution and pooling process worked very well. Area 2. We have 2 areas showing Omuroyama-like. Okay, what are they? Well, actually, this mountain is also named Omuroyama. And this is the one I already showed to you. This Omuroyama is, well, exists here. Well, in Google photo, this photo is taken in the winter season. This one is summer season. Well, the frequency is very, very low in the case of Google photo. We sometimes see the boundaries like this. And okay, this is named, say, Yahazuyama. But we can see the shape is a little similar. This is Hakone area, area 3. Hakone is Hakone National Public Park, sightseeing place. And this area is near to Yokohama area. I always say that you have you may have visited this area if you attended at the IGAS 2019 conference held in Yokohama. Yokohama is located on the right-hand side of this map. This is, say, 2 hours far from Yokohama. I see some of the attendees visited this area, Mount Fuji, and also this area. Many people visited this area. And I also visit this area to enjoy the nature many times. But I didn't know why this is red, showing Omurayama. Well, this is a Google photo. Okay, this is the shape. The shape is, yes, very similar. This one, very similar. These mountains are named Futakoyama, meaning twin mountains. And from viewing from Tokyo, we can see these mountains like twins. So Futakoyama, twin mountains. But it is not sure from Tokyo that these mountains have this shape. But with this photo, yes, the shape is, yes, can be Omurayama storage mountain. And actually, the size is much bigger than the teacher Omurayama. The system is successful in finding these mountains. We look into the neural network. Well, this is the convolution filters showing the amplitude in grayscale and the phase in color. And they are complex values. Before the learning process, they are initialized at random. We have prepared 9 filters in this case. For the east-west gradient input chunk, and for the north-south gradient input chunks. So this is before the learning. Then after the learning, this is the after. Before, after, before, after. Well, we can see some of the filters have got whiter. Number 1, 2, 6, and 9. And these white filters show their significance in the processing. The darker ones are less significant. For example, this one, the top right-hand side. This one is one of the white ones, so significant one. And in the phase, we see this part, the upper right side is green, almost green. So this value. And on the other side, it is pink or blue here. Then this filter has a shape of this kind. The phase value shows the shape. So this is the shape of the filter. Then this filter is specialized to extract this shape included in the local image. In this way, we can interpret what happened in the neural network. And at the bottom, we can see very similar but a little different filter values. Okay, this is the process in the neural network. Well, as the concluding remark, more important of this kind of processes. This view graph is made by Motooka-san in JAXA. The horizontal axis shows the sword width observation. The vertical axis shows the resolution of the observation of JAXA satellites. JERS-1 was the very nice one in the very early days. Aris worked very nice until the earthquake 10 years ago. And now Aris 2 gathers the data every day. And in the near future, not 22 probably, but 23 or 24, we will have Aris 4. Wider sword and high resolution are obtained with this sensor. Then we can get the data, for example, around Japan, we can get the data almost every 14 days. The observation is very frequent. So high resolution in space and high frequency in time are realized. Then we can and we should deal with more information. And the society, the modern society, is a data-driven society. As Professor Aris said, many satellites gather information, and the data plays a very important role in our society in the decision of our directions. And then the significance is increasing more and more to obtain the various data and prepare the data in the optical data, infrared, so on, SAR data, including the phase, polarization. I didn't say anything this time on the polarization, but it is also very important, as Yamaguchi-sensei said 2 weeks ago. This view graph is provided by Yamaguchi-sensei. So more various data to be gathered and to be processed. Then we can realize a more safe and comfortable society. So that's all today. Thank you very much for your kind attention.
Okay, thank you, Sensei, for your presentation. It's a nice presentation and very interesting about the method of convolutional neural network in InSAR and PolSAR data. And how about we continue to the question and answer session, sir? Okay. We have the question here. It's from Mr. Muhammad Isa. Professor Hirose, is there any recommended interval for SAR data capture to understand the changes or give clarity on the disaster predictions? Please, sir.
Well, more frequently, the better. Well, yes. Of course, if the frequency is very, very high, so interval is very, very short, then the changes can be very small. But it is related to the resolution in the range direction and the azimuth direction. And we aim to realize shorter interval, higher frequency. If we don't need this data, then we just omit them and we choose some of them. Well, for this purpose, we need many satellites launched, and international society should cooperate closely.
Okay, thank you. Maybe we can continue to the next questions from Mr. Muhammad Arif Munandar. Professor Hirose, in your slide, you evaluate results CNN model manually. Do you have any idea if there are many data to evaluate? I mean, automate.
Yeah, it's very difficult to realize the automatic evaluation. Yeah. Okay. Probably you have that kind of difficulty in your research. Eh? And well, in the first stage, we have to do the evaluation manually by using our own brains. But when we gather more data, then most of the processes can become automatic. Well, I mean, the decision, in this case, the classification, can be done based on the already decided data. In particular, when we gather many kinds of data, optical or the L-band SAR, X-band SAR, and so on, different kinds, then they are helpful to evaluate others to one another. And this is also very helpful to semi-automatic evaluation or to construct that kind of system. But now we are at the starting point, and we have to do the evaluation basically manually.
Okay, thank you, sir. I think we have a last question from Muhammad Iqbal. Professor Hirose, I would like to know, how do you process the SAR data to neural network? Do you use feature extraction first? Yes, sir.
Well, yes, I think so. Well, feature extraction is one of the most important tasks of neural networks. Well, basically, neural networks deal with non-symbol information. Symbol means something written by letters, characters, numbers. So the language is one of the symbol or information. But in this type of observation, we will measure something different from the letters, or the data is digital, but the data itself is more analog, and distribution in space and time, that is the data. And it is not translated or transformed into symbols. Once it is processed to be transformed into the symbols, then the conventional logic can deal with the data. The feature extraction is the most important point to bridge the pattern, non-symbol features, information to the symbol information. And this often happens in anywhere. For example, in the customers purchasing activity analysis, or in the mobility of the people, many. So in this sense, the feature extraction is the first one we should do after the acquisition of that data, raw data.
Okay, thank you, Professor. Oh, we have another question in chat room from Mr. or Bapak Arifin Nugroho. Professor Hirose, sorry for these dumb questions. What is the benefit of using your approach as compared with the conventional way of classification approach?
It depends on the conventional ways. Well, probably, 2 weeks ago, many people attended at Yamaguchi-sensei's lecture, showing, I think, the polarimetry and its signal processing, showing this is double bounce, this is surface bounce, and so on. And in that case, I think they mainly use the matrix decomposition, or the model-based decomposition. It works very well and very strong, very nice. And in that case, sometimes, the original one dealt with or generated 3 classes, so volume and double bound, surface, scattering. They corresponded to the red and blue and green. Very nice to show the beautiful map. And sometimes we introduce or not they, but we, or many people, introduced helical. And also Yamaguchi-sensei recently proposed more features in the polarization, 5 or 6 in total. In that case, which color we should use is a big problem. For 6 features, red or blue, or which one, that is a problem. This happens because our brain decides this is the sea area, or this is the town area. This is the town area of north-south facing buildings, or this slant direction buildings and so on. And in this process, our brain works very adaptively. But it will be very nice if we can include this adaptive process also into the SAR processing system. So recognition or decision. And that kind of task is realized very nicely by using neural networks. If this question means the neural networks to the a little less adaptive way, then this is my answer.
Okay, thank you, Professor. Well, I think the time for Professor Akira is over. Thank you so much once again. Arigatou gozaimasu. Such an honor to meet you here, sir. Okay. Once again, I inform you, e-certificate will be launched at the end of this webinar. And then if there's any question to our lecturer, please follow the application link on chat room. Okay, for our third lecturer is Professor Feng Xu. Hello, Professor Feng Xu. How are you today? Hi. Okay, nice. I'm fine, thank you. Nice to meet you here. Professor Feng Xu is from Fudan University, China. Okay, please, Professor, your time is about 1 hour, and after that, we are going to continue with question and answer sessions. Please, sir, the time is yours.
So can you see my slides?
Yes, I can see it.
Okay, so sound is okay?
Yes, the sound is okay.
Okay, cool. So thank you, Rika, and very happy to be here to give the tutorial by invitation of my friend Joseph, and also together with Akira. Also, is very good friend. Okay, so my talk is titled Deep Learning as Applied in SAR Imagery Interpretation. My name is Feng Xu. I'm from Fudan University in Shanghai, China. And so the work I'm presenting today is, can be found on our GitHub website. So it's all open sourced work. So the outline of my talk. So first I'm going to introduce a little bit about SAR information retrieval and talk a little bit about deep learning. And then the major part is a introduction of some of the works we have been doing over the years in SAR image interpretation. So I put like a few examples here. So, and all of these works are published, and most of them are open sourced. So if you are interested, you can check on the website and on the papers. So first, so the major motivation of our work is to meet the development, the rapid development of SAR technology, in particular space-bound SAR remote sensing. And as we can see that the data of our SAR image has been developed rapidly. So there's two trends. First is higher and higher resolution, and second is higher dimension. So it includes, like, for example, multiple polarization, multi-temporal, or multi-incidence, multi-aspect angle, etc. And also we see that the volume of SAR image obtained routinely has been exponentially increased over the past years, because we can see that number of radar satellite is increasing. In particular, in this year, we can see that there are few commercial satellite. The small SAR satellite is being launched, and we can see that the golden age of SAR image processing and remote sensing application is coming. And so the key is that, like, how to process or how to develop the automatic approach for SAR image interpretation, how to extract information from SAR images. So that becomes the key of the research. And so we usually compare SAR image interpretation into a optical image processing. That's also called computer vision in computer science domain. So compared to computer vision, we can see the difference is originated from the sensor itself, right? We compare the imaging radar with optical camera. We can see that there's many difference. And so as a result, we can see that the image also appears to be very different. The same target, the same object in the optical image versus in the radar image, that's a very big difference. And so that's one challenge here is that because as a human, we are used to understand the optical image, but not directly can interpret the radar image. So here, this table summarized some of the difference between these two forms of image. As we can see that for example, in frequency band, the basic scattering, the scattering features the two sensors captured are totally different. And besides, the imaging mechanism is also different, because for SAR imaging, it's a phase coherent approach versus for optical is like a lens focusing approach. And also because one dimension of SAR is in conventional radar is for ranging, right? So one dimension is ranging, and the other dimension is azimuth. But for optical image, usually it's elevation versus azimuth. And one more difference is also very interesting, is that the resolution of SAR image is constant, does not change with respect to distance to the object. But this is not true for camera, because for camera it's proportional to distance, right? And but the comparison here, the purpose is to see like how we can get inspired by the development of computer vision area, because in that area, one very popular technique is called deep learning has achieved great success, right? And it has achieved many successful applications, right? Such as face recognition and automatic like driving and so on. And so for deep learning, is basically I would say in essence it's curve fitting. It's basically it has a very strong, powerful, fitable network. Network basically is a function, right? It's a very complicated function with a lot of parameters, tunable parameters, and so basically you're trying to fit the network to the data, and so that essentially is very heavily relying on the training examples, and so for this is one of the limitations when we try to apply deep learning to SAR image. And so sorry, let's see. Okay, so let me see. There's an issue here. There's recording. Okay. Sorry. Okay. Sorry, let's continue here. So just in the previous talk, and Akira has give very nice introduction about the neural networks, right? And so I'm going to just go to talk a little bit about the convolutional neural network. It's called a CNN. So it's basically it's one type of neural network. It has very special designed network layers. It's called a convolutional layers, and this was inspired by the human visual cortex process. So for human visual information process, we can find there's two principles. First is spatial in translational invariance. So for the same target for the same object in different place for visual information, we see the same thing, right? So this can be implemented by using convolution. And the second is that for human visual perception, we can easily use different use some of our experience to interpret a new object. If we see a new object, we can easily interpret it as a combination of components which we already know, right, in our past experience. So this is called the compositionality, and this principle can be implemented using deeper networks, because if we have many layers, network layers stacked up, and it has this exponential growing capability of representation, which is mimicking this principle. For specifically for convolution layer, in fact, it's very simple, right? So for conventional neural network is called a fully connected neural network. So basically, for each input neuron, let's say we input an image. Then for each pixel, we have to have one neuron to represent that pixel. Then for a fully connected neural network, each neuron in the first layer are connected to each and every neuron in the second layer. So for that, we will have a huge number of unknowns, so parameters of the connections, right? So it's very dense connected neural network. For convolutional neural network, so basically we have two steps of simplification. First, we restrict these connections to be locally connected, which means for each neuron, we only connect with the neuron in the first layer in the neighborhood pixels. So for that, we have we reduce a larger number of connections. And the second, we apply another constraint. Basically, is to constrain that for all this connection, for all these weights or the parameters, we restrict it has to be translational invariance. So which means this black, red, green, and blue has to be equal to each other. So this layer becomes a convolution operation. And but in the meanwhile, we allow that we have multiple channels of these layers. For each channel, it allowed to have different weight, convolutional weight. It's also called a kernel. And so this is basically convolutional neural network layers. And combined with this network, we usually we also put called a pooling layer. Pooling layer basically is to do for example, here we have a network layer, and then do a max pooling of 2 by 2 to become like a undersampled of this image. And for this each particular window, we only take the maximum value to keep the maximum value. So that's called a pooling layer. So this animation shows how the convolution was computed. So basically, it's quite a simple convolutional operation. So this is a basic idea of neural network, convolution neural network. So I usually for a 2-hour or 4-hour tutorial, I will expand a lot about this basics. But this 1-hour tutorial, I will skip that part. So if you are interested, there are many reference online. You can search online to know about these neural networks. So next, I'm going to give a few examples like we did in the past, with regard to how to use deep learning to interpret SAR imaging. First example I'm showing is a parametric SAR classification. This is quite a straightforward task, and is very easy to use convolutional neural network to do it, because image classification is also a very classic task in computer vision. So this work, we basically directly use a very simple, I think it's 6-layer convolutional neural network. And this means convolution layers, and this means fully connected layers. And we did very few processing. I think we only pre-processed the PolSAR image of, I think it's a T matrix, right? It's called a coherency matrix, and mapped into a 6-dimension vector. And it's also, I think it's normalized from 0 to 1. And then input this form of data into the neural network. And so we can use this classic SR image as an example. So we can handpick some of the regions. I think this regions that shows with a number as the samples we picked, handpicked as a training sample. For example, we pick this area as a sample for sea surface, and this is for vegetation surface, and this sample will be used as training sample. And I forgot to mention that for this particular example, the neural network takes in a neighborhood window. I think it's a 12 by 12 neighborhood window, and input the data, and it output the class of this center pixel. So it's basically a sliding window approach. So this example, we can see that so it comes out quite good. Actually, we can see that all these most areas are classified correctly. And then here is another work. We expand this approach a little bit. We introduce a complex value in this neural network. And for complex value, the neural network, Akira is one of the pioneers in this area. So for this work, we basically to design a complex value convolutional neural network. So it's very similar to the one I just showed, but except all the data, the weights, and the activation functions are defined in the complex domain. And also we implemented this algorithm. I think it's in MATLAB, and if you're interested, you can see the paper and the code. And so the question here is like how a complex value CV CN versus a real value CN, right? The conventional one, because the only difference is that the operation of the data is different, right? So here notice that what I mean is that so all the data, like originally we can see that for a PolSAR image, some of the channel, right? The channel is off diagonal element of the matrix. It's complex numbers, and for complex numbers, you can either treat it as a real value, right? You can treat it as a real and imaginary two real channels. So we can use conventional real value CNN to process, or we can use this complex value CNN. For that, we have to treat each complex channel as one complex number, and which means that they have to be computed together in the complex domain. And these two networks, we specifically designed the network structure so that the number of layers, the number of tunable parameters are very close to each other. So we use this also classic Flatland SR image as a benchmark. So for this image, we can see it's about 18 type of vegetations, and it's also has a label image, and we compare the the result of CVCN and RVCN, as we can see that there's a quite a big improvement in terms of the accuracy. Okay, so this image shows the kernels of the first layer of the CNN learned by this neural network, and we visualized this kernel with poly RGB coding, and we can see that the different kernels respond to the corresponding type of terrain surfaces. And we first expanded this method to parameter inversion. So this case showing here is to inverse the tree height from polarimetric interferometric side data. So for this, we also select a few pixels as a training sample, and to train this CVCN to do this tree height inversion. And compared to the regular, I think is model-based method, and we can see that it has pros and cons. And another example is we did with this PolSAR images do SAR image colorization. Basically, we're trying to convert a single pore or compact PolSAR image to fully polarimetric image. And how to do that? We use 4-pore image as a training sample to train this conversion neural network. And then we test it with another area of the image. The structure basically is a regular CNN. So this part is a CNN, which is a feature extractor neural network. And then we stack this multi-scale features of each layer to be a hypercolumn of feature vector, and then feed it into another feature translation neural network. This one, I think, is a fully connected neural network. And the output is the number of parameters unknowns, which was required to reconstruct the fully polarimetric matrix. So basically, this is how we reconstruct 4-pore SAR image from single pore. And this figure shows the features that are extracted from a single channel VV pore SAR image. And so this basically explains that how this feature extraction neural network was used to classify different type of terrain surfaces. And for this specific each type of terrain surfaces, we can have a experience on what type of polarimetric scattering it usually has, and we can assign that knowledge onto this particular area. And let me see. So this figure shows that this neural network. So here, I think it's finally can reconstruct this 4-pore data, and with this reconstructed data, we can plot the feature space, which is H alpha plane, and we can see that different type of terrain surface has different distribution. And if we compare to the ground truth, which is the bottom right one, and we can see that the distribution locations are pretty much right. And so overall, this is a final result. This is the original true 4-pore SR image, right? And we pick the pixel on this yellow box pixel as a training example to train this neural network. And then we take just one channel of this image, this black grayscale SAR image, one channel, feed into that neural network, and it automatically reconstruct this 4-pore SAR image. And if we enlarge these places, and we can see different terrain objects are recovered pretty well. And this is another case, another image, right? And we take a brand new image, and we just use one channel to input to this neural network, and it can reconstruct the 4-pore SAR image. And this is a paper related to this work, and the code can be found on the web page. And another similar similar work is to segmentation of SAR image, and this is for a single pore SAR image. So basically, we try to do a very fundamental segmentation of the terrain surface of given one single pore SAR image, and this work was specifically done for the Chinese government 3 GF3 SAR image. So we employed a basic approach. So it has a backbone network, is Deep Lab V3. It has encoder decoder structure, and this is a basic as a network structure, and it also has called Aperture spatial pyramid pooling networks. Anyway, so we constructed a data set. This is called a PolSAR maps data set. So it contains, I think it contains about 10 things of GF3 SAR image, and it covers about a few cities in China, in different regions in China, and we match up with this SAR image to the Google map, and so that, and also the Google map and the digital map, and from that we can extract the label information, automatically extract like where is the water, where is the building, and where is the forest. And so this we trained our neural network with this benchmark data set, and it turns out to be pretty good in many scenarios. It can automatically segment this water, vegetation, and also buildings and the road. And we also compared with other existing approaches, and this work is also published, and data set is also released. So this is for image segmentation and classification. Next, a few examples I'm showing like how to do SAR target recognition with deep neural network. Initially, we did quite a straightforward approach. So basically, we input this SAR image into a convolutional neural network and basically train the network and see how it works. And so first, the benchmark data we used is the InSAR data set. It's originally obtained by the Lincoln Lab, and it has, I think it's 1 foot resolution at X band, and it has 10 vehicle target with all different aspect angles. And we first devised a very simple neural network. So it's all convolutional, means that all layers are convolution layer without fully connected layers, because we trying to reduce the number of tunable parameters, and we also use the data augmentation strategy, and then this figure shows the kernels learned by this neural network, and And we can see that some of the kernels show some features of edge detector. This bottom line shows feature mappers. And for regular testing condition called a standard operating condition, which means that all the configurations are same for training and testing. And we can see that this confusion matrix and the final accuracy is about 99.99%. It's very good. But this there's a problem with overfitting when the training sample is not sufficient. It may get overfitted, so that we need to test how the network generalize at different condition called the extended operating condition. For example, we change the incident angle to 30 degrees, see how it performs. And we can see that the performance is dropped to 93%. And the second case we tested with what if the target has a configuration change, means that the vehicle has a little bit different, and see how robust the classifier works. And it turns out to be quite robust for this scenario. And we also tested with another case is that I think the vehicle has even larger difference, but we can see that it's still quite robust. So overall, we compared our method with our state-of-art, and all this state-of-art method by then are all non-deep learning method. So it's all non-conventional method, and we can see that our method outperforms with existing approaches. Then we did a little bit more work to construct an end-to-end demonstration. So it's basically first we need to detect object from the entire scene, and then we try to do the classify of each potential area, right? So for detection, so it's basically a binary classifier, right? It's a target versus background. So the same approach can be used for detection. And finally, we were able to demonstrate from end-to-end SAR image automatic target recognition. The paper is published and codes are also available here. For sea surface target, we also did quite a few works. So for sea target ATR, the key is like how to implement a highly efficient method. So we employed a multi-stage strategy. So first we try to do a segmentation, means that we try to exclude the land from sea. And second, we try to detect brightest pixels from the background using a conventional method like CFR detection. And then we try to discriminate false alarms from the pixels, and then finally we try to perform target classification. So first we devised the shape ATR framework, just I mentioned, and this also published work. And so first step is to do segmentation. So it's basically binary segmentation. It's trying to classify sea surface from land surface. And next we did a detection. Basically we use CFR detection. The result is quite good. And so next when we try to do classification, we need a label label of each target, right? So we use a matchup database. So it's basically we match the SAR image with the AIS image. Because the SAR image we already have detected each target, and so we have this coordinates, is latitude and longitude and the time of this particular target, and so we can match it in space and time with the AIS record. Right? AIS is a system for the ship to identify themselves to the satellite. And so we have this build up this data set called the PolSAR ship, and it's basically I think we have like 8 type of different ships, and so finally we can do from end to end, right? Input an entire thing, and output is the detect and classify ship target. Okay, so this is a simple case of target recognition. So here next I'm going to introduce a little bit about representation learning. Okay, so this is maybe not that relevant to deep learning, but it's important to understand how SAR image was the mechanism behind SAR image. So here one of our work is to develop called a speckle representation model. So basically we use a discrete scatters to represent a 3D to represent a SAR image, right? So we basically treat each pixel as see overall coherent summation of a number of random scatters. And so this model is called a generalized Gaussian coherent scatter model. And with this model, because it's a statistical and physics based model, so we can tune this model to generate a different type of SAR speckle, SAR clusters, right? And here shows, for example, the top row is real SAR images, and the bottom one is the generated SAR image of the similar type, and this we are still working on this. We're trying to incorporate this model with together with a deep neural network. And speaking of the speckle filtering, we developed called a despeckling neural network, and this is a neural network structure. So on the left side is a regular convolutional neural network. So input is a small patch of SAR image, and output is a PDF of this area, RCS of this area. So basically, we're trying to estimate the real RCS given a patch of SAR image. And so this neural network is trained with called a specifically designed loss function. So this loss function is devised based on I think it's called the product model of speckle. So I'm not going to the details of this work. So this is the left side of the neural network. So basically, input is I think it's 12 by 12 window of SAR image, and output is a PDF, like what's the actual RCS distribution behind this SAR image. And we trained with this network, we simulated the data. We use 3 different types of masks. So this is homogeneous speckle, and the second one is I think it's an edge with an edge like two types of homogeneous areas, and the third one is a bright spot. So it's also a common case in SAR image. And with this simulated data, we train this neural network, and then we can apply this neural network for speckle reduction. And this show a two case, right? The left side is the original speckle SAR image. Right side is despeckled SAR image. And we also compare the CNN-based despeckling with other type of conventional speckle filters, right, like Lee Sigma or Eden filter. And we can see that so this CNN-based filter works as well as conventional methods. And this is a paper about these two works. And next is an interesting work. What we call is targeted representation learning. So basically, we try to construct a target feature space given a few training samples. For example, we have this target space, which is constructed with a dimension. Dimensions has a specific physical meaning. For that, we can able to interpret in the target feature space to generate different samples. And this is a neural network. It's a generative neural network. So I'm not going to talk the detail because of I don't have much time left. Anyway, so this is a deep generative neural network. So input is opposite direction of CNN. For generative neural network, input is a label and the orientation angle, and output is a generated SAR image. And so for this, we construct a target space, and we can see that so it's a similar target are located in the similar area, and this is the images which are generated by using this network, and with this we can automatically perform a classification of a SAR image, and also we can use this network to classify unseen target, right? If we have a target which we never seen before, and we can input to this neural network, and it will map to the feature space. And given the position in the feature space, we can guess what type of target it is. So finally, I'm going to show some most recent work on few-shot learning. Few-shot learning basically means that how the network can work given a very limited number of training samples. So as I mentioned that when we apply deep learning in SAR image, the major bottlenecks first is SAR image is different from optical. So you may consider the spatial handling of SAR image. Second is that it's a training sample order of magnitude less than optical, right? For SAR image, usually we have 1,000 training sample is considered quite a lot, but for optical it's like millions of samples, and the third is that so SAR image is quite sensitive to observation, in particular the incident angle. If we look at the different angle, we can see that the target scattering feature may change rapidly, but this was not the case for optical image. So for that, we even more critical even more critical to have more training samples. So here I'm showing like two type of challenges. First one is what if we have missing observation angles, right? For example, for each particular target, what if we have only few observation angle available? Like how to do this? How to do this? And so for this, we proposed called aspect interpretation using the adversarial autoencoder called AAE. And so basically it's kind of a adversarial structure. So we have one neural network is in charge of generating fake SAR image, and another neural network is responsible for discriminate this fake image from true SAR image. So these two neural networks is kind of compete with each other, so that both of them can be improved. And this strategy was used quite often in computer vision area to generate a fake image, like a fake deep fake, right? If you heard of it, it's used to generate a fake human face image. And so we use a similar approach to generate a SAR image. And here shows some example, like this is one vehicle at a different aspect angle. Left one is real, right one is fake. It's generated by neural network. Right, and so here is a second case. This is another case, right? And we can see that it's quite realistic, right? And for visually, it seems almost the same, almost similar. And so with this neural network, we able to interpret in the aspect angle, right? I just mentioned that the first challenge is that what if there's a missing aspect angle? Then we can use this to interpret these aspect angles. And with this, we can generate more training samples, and we can improve the ATR algorithm. For example, for this case, the classification accuracy can be improved. I think it's a few percentage. This paper also is going to be published soon. So type 2 challenge. What if the one target is missing, entire target is missing? And for that, we have to resort to other type of information. So one approach is using EM modeling. For example, here we show example. We have 9 target which is have a known target, but one T72 is unknown. For this unknown, we have if we given a geometry CAD model, we can simulate SAR image, right? So this is a case showing the simulated image versus the true image. But for simulated image, it has quite a different styles, right? In particular, this speckle effect is very different. So for that, we propose a pre-processing method to suppress these non-essential factors. So after pre-processing, these two images looks very similar. And in particular, in the feature space, so these two simulated and real data samples are aligned together, so we can use the simulated to train the neural network. So finally, we are able to achieve like 80% accuracy for this called zero-shot learning. It means that we don't have any training sample. See, here is another case. I think I'm quickly go through because I don't have time. So this is basically aircraft detection and recognition, and this is a paper about this. So it's a regular neural network, but with scattering enhancement. a final case I'm showing here is how is to translate a SAR image to optical and vice versa. So we use what they call a cyclic GAN. GAN is generative adversarial neural network, and we use it to train image pairs of SAR and optical. And after training, this neural network can use to translate SAR image to optical. Here shows an example, and here another few examples. This is a farmland SAR image input. Output is a translated optical image, and the light column is a true, actual, real SAR optical image. So it looks quite close here. So as a summary, so basically today I'm presented some of our work on SAR target recognition and image interpretation using deep learning, but there's still challenges ahead. Basically, we have very limited training samples. So one of the approach we currently working on is trying to combine physics-based approach together with data-driven deep learning methods. So we recently have published a book, but it's in Chinese. Anyway, so if you are interested in our work, you can visit our webpage and website. Or most of the work are open sourced, and you can find the code here, and also you can check our papers. Okay, thank you very much for your attention.
Okay, thank you very much, Professor Feng Xu. Very nice and interesting presentations. Well, now we are going to have a question and answer sessions.
Okay.
Okay, let me share my screen. Okay, we have from Mr. Tommy Ardiansa. Professor, what the better polarization, VV or VH, to detecting object, for example, to identify lodging in forest? Please, sir.
I would say in forest, I'm not sure, but because the forest scattering is usually shown in VH channel, right? So the background is shown in VH. So I probably not sure. For this case, I'm not sure, but for maybe for other scenario like sea surface, then I would go with VH. Right, but usually for spaceborne SAR, there is no option as a VH channel. You at least get two channels, right? VH or VV, or if you have single channel, is copol, right? It's VV or HH. Right, I think.
Okay, thank you, Professor. Well, in audience here, is there any questions to Professor Feng Xu? I will open the discussions. No? Well, I think the time is over. Professor, thank you so much for coming in our webinar. It's such an honor to meet you here. Okay, for the audience, please download your e-certificate. Follow this link on chat room. And this link available until 5 p.m. Jakarta time or 7 p.m. Japan's time. And then you just have to put your name and then click download to have the certificate. Well, I think the time is over. Now we are going to have a photo sessions. Please open your camera. This is our last photo sessions. Two co-hosts, please help me to screenshot. Okay, let's start from slide 1. Okay, 1, 2, 3. Smile to the camera. Okay, thank you. And then for second slide, we have 6 slides because we have 139 participants. Second slide, please smile to the camera. Okay, and then the third slide. Please co-host help me to screenshot all the slides. Okay, thank you. Thank you. Don't forget to download e-certificate on application link. And then just put your name and click download. This certificate available until 5 p.m. Jakarta time or 7 p.m. Japan's time. And please always follow our information about InSAR 2021 in our website on epsar2021.org. And for our next event of pre-conference InSAR 2021, we have third tutorial series that will be held on 8 April 2021, and we will present our lecturer include Dr. Ing Wahyudi Hasbi from Lapan, and Professor Wataru Takeuchi from Tokyo University, and Professor Atsushi Higuchi from Chiba University. And of course, beside that, we have a Marathon dan Bunga Rampai Penginderaan Jauh Indonesia that will be held on 6 May 2021. And you can send the abstract until April 30, 2021. And don't forget to send your abstract to InSAR until 30 April 2021. Is there anything else, Professor Josaphat, to about the information?
Yeah. First is thank you very much to Rika-san, also Professor Akira Hirose, Professor Feng Xu, and also Professor Aris. Yeah, and today I think you learn much, yes, about the synthetic aperture radar and the trend of the synthetic aperture radar, yes, including the deep learning, neural network, and I think it's many, yeah. And I hope all of you know more about the synthetic aperture radar and the APSAR, yes, Asia Pacific Conference on Synthetic Aperture Radar. We hold this symposium every 2 years, yes, and I hope next November, yes, many young scientists and student and of course the researcher can join us. That the abstract deadline is 30 April, and I hope in the future, 2 years later, I think is some of you can join, and make the APSAR more, more attractive, yeah. And I think it's every year is about around 400, 500, yeah. And our target is even if COVID is, yes, our target is around at least is 400, yeah. Please join us and let's share together, yeah. And yes, please don't forget 2 weeks later, yes, like Rika-san mentioned that we will hold further, tutorial, yeah. And I wait all of you and let's learn together, yeah. Okay, thank you very much, and yeah, thank you very much again to Professor Hirose and also Professor Feng Xu. Yeah.
ありがとうございました。
ありがとうございました。はい。
Okay, thank you so much. Thank you so much to our lecturer, our committee, and to audience, and to participants. I'm Rika Hernawati. See you again, and goodbye. Thank you.
Okay, thank you very much all. Yes, and keep healthy. Yeah.
Thank you, Professor Josaphat.
Oh, Pak Arifin juga ada. Yeah, terima kasih. Thank you very much. Yeah. Terima kasih semua para panitia ya yang mengadakan tutorial ini.
Terima kasih, Pak.
Oh, ini ada Pak Edward. Yeah, terima kasih. Yeah.
Professor Hirose, thank you.
Yeah.
Terima kasih, Pak Arifin. Pamit, Pak.
Mari Bapak, sampai ketemu lagi.
Pak Josapat, terima kasih banyak atas kesempatannya.
Ya,
Thank you.
mudah-mudahan yang muda-muda biar pada kenal dengan expert ya, biar tahu.
Iya.
Ya.
Terima kasih banyak, Pak.
Dimanfaatkan ini. Tolong ini disampaikan ke teman-teman semua ya, agar
Siap.
semakin banyak orang Indonesia dikenal nanti. Ya.
Siap, Pak.
Terima kasih, Prof.
Pertama kenalan dulu, nanti agar jadi terkenal. Ya. Dulu itu.
Terima kasih Mbak Rika.
Terima kasih, Pak. Saya live, Pak.